Okay, so I think we can start. So it's a pleasure to announce Caitlin Casey. She's now our neighbor at UC Irvine, and she finished her undergrad at the University of Arizona. And after undergraduate degree, she went to University of Cambridge as a prestigious Gates Scholar. And after finishing her PhD with Scott Chapman, working on 7-millimeter galaxies and high Hewlers, she got another prestigious Hubble Fellowship and moved to University of Hawaii. And after expiring her Hubble, she just started a new fellowship at UC Irvine called McHugh Fellowship in Cosmology. And she became well known in the field by her work on warm Eulers and a bunch of properties of 7-millimeter galaxies, started from her thesis, and then I guess she increased sample of 7-millimeter galaxies and warm Eulers by order of magnitude or so, and she's been working on all kinds of issues related to very star-forming galaxies and high redshift, and she's going to talk about them today. And I guess her title is Mergers or Math. So,
great, thanks, Tushan. Yeah, so I decided to make my title as controversial as possible. This is a big debate in the area whether or not infrared luminous galaxies are all dominated by major mergers, or if you don't need major mergers at all to explain infrared galaxies in the early universe. So yeah, it's great to be here today at UCSD. It's a pleasure to talk to an audience which is pretty diverse. You know, I know some of you are experts in galaxy formation and evolution, but others of you are experts in other things. So I really like it, you know, since it is a diverse group, if you just go ahead and interrupt me if I don't make sense at any point, and it'll be great. I'm always pleasantly surprised when a talk turns into a discussion. So what I want to discuss today, I'll split up into 3 sections. The first of which, I'll explain some of the motivations for why it's interesting to study starbursts, infrared selected starbursts in the first place. Second, I'll discuss some of the practicalities of studying infrared starbursts and some of the difficulties and observational hurdles that we experience. And last, I'll discuss the future of submillimeter surveys in resolving cosmic star formation out to very high redshift, and what dust really means in terms of the entire cosmic star formation rate density of the universe. So motivation first. We know that star formation takes place in dusty environments. We see this in our own Milky Way, but also beyond the Milky Way, farther afield. This is a schematic of the cosmic background radiation. You're probably all too familiar with the cosmic microwave background, but there are also these components emitted in the optical and the infrared, which originate from extragalactic sources, galaxies. And we've come to know quite a bit about the cosmic optical background from facilities like the Hubble Space Telescope, which sheds great light on cosmic star formation out to very early epochs in some of the earliest galaxies. But when we look in the infrared, we've been much more limited, to be honest. And this has been due in part to limitations in observing. But what we want to do is kind of move into a realm where we understand the infrared component just as well as we understand the optical component, since the relative emission in both regimes is evenly split. So what type of galaxy emits in the infrared, and is there any reason to think that they're different than those that emit in the optical? The initial study of infrared luminous galaxies started, I would say, with the infrared astronomical satellite launched back in the 80s. This is a great facility discovering thousands, many hundreds of thousands of point sources all across the sky, most of them nearby, really exquisite systems emitting in the infrared. And when we looked at the same places as the sky, in the optical, what we saw was that nearly all of these galaxies were major mergers. All ultraluminous infrared galaxies, nearly all, are major mergers. And just to throw some terminology in front of you now to avoid it later. You'll often hear these terms in the high redshift dusty galaxy world. LIRG, luminous infrared galaxy, that is a system that has an infrared luminosity of greater than 10 to the 11 solar, or about a few 10 solar masses per year star formation rate. ULIRG, ultraluminous infrared, and high LIRG, hyperluminous infrared. So those are the classes of infrared luminous galaxies split by luminosity. And then in the high redshift world, we often talk about some millimeter galaxies, which is a term that's often used loosely. It can have a strict definition, but it just refers to any ULIRG type system at high redshift detected in a millimeter. So over time, after we studied these local systems in detail, the schematic evolutionary diagram was developed to explain these very dusty starburst galaxies. And this was presented rather concisely and well by Dave Sanders in '88, where you have two merging gas-rich disk galaxies, not unlike the Milky Way, that collide and ignite a very heavy episode of star formation, and where there's a lot of production of dust. And this is what's called the ULIRG phase, when a lot of the emission from young, hot stars is absorbed by dust and re-radiated in the infrared. And so that's the ULIRG phase. And after that phase, you might have a black hole, which is accreting material, a supermassive black hole, and obscured AGN or an unobscured AGN leading to a quasar. And after the black hole stops accreting material, you might settle into a massive early type elliptical galaxy. So this was the explanation for the formation of local elliptical type galaxies. And this is what I refer to as a classic evolutionary scenario for ultraluminous infrared galaxies. And it really came about from that IRAS sample. Looking at it a bit more quantitatively, this is a schematic of the star formation rate against cosmic time. From the early pre-merger stage, you get star formation rates of a few tens, maybe 100 if it's a star-forming galaxy. But during this ULIRG phase, which is very short-lived, you get incredible star formation rates, which often exceed the star formation rate previous to the merger by factors of 10 to 100. But since the star formation rate is so quick that maybe you use up all of your star-forming fuel very quickly, you exhaust all of the gas, and then you have no more stars to form. Perhaps a black hole kicks in, and you have AGN feedback, which expels gas, and you settle into an old population. So again, locally, all infrared galaxies, all ultraluminous infrared galaxies are mergers. But the question we want to answer now is this the case at high redshift? So this is a schematic of the star formation rate density with redshift, or Lilly-Medal plot, where you have contributions from different populations to the star formation rate density of the universe. At redshift 0, these ULIRGs and LIRGs contribute very little to cosmic star formation, but these are known mergers. At early epochs in the universe, past redshift 1, they actually dominate, they contribute significantly, if not dominate, the total. Yes?
They've already gone through a significant amount, the ULIRGs of star formation. In other words, are they in the post, sort of like he said, they don't contribute much?
Yeah, they don't contribute much at redshift 0. So in other words, they're just very rare. Normal Milky Way type galaxies are forming more stars per unit volume.
They did a lot of star formation?
Yeah, so I mean, what was a ULIRG at high redshift is no longer a ULIRG, because the time scale for that phase is very short. So the question is, since these are so important in the early universe, are they also mergers? Another question we want to address is what the contribution is at even higher redshifts. So there's good estimates from the optical due largely in part to the Hubble Space Telescope, of what the universe is doing in terms of star formation out to very high redshift. That perhaps it peaks at redshift 1, 2, all the way out to 4 perhaps, and then drops at higher redshift. You just don't see stars forming. So this is starting to probe the epoch of reionization. But what we don't know is what the contribution from the dust is doing. At best, we have that nailed out to redshift 2, but not beyond. And since half of the starlight in the universe is being reprocessed into dust emission, I'd say it's pretty important to figure out what the dust is doing at high redshifts. So just to take you into an alternate view from the classic evolutionary scenario involving mergers, is this other alternate picture of how they could have come about at high redshift. So in the early universe, the intergalactic medium is more dense, and the cold gas that you need to form stars might have had a more efficient mechanism for being fed onto galaxies, producing higher gas fractions and higher star formation rates. And this is reinforced by some the theoretical work done with the old gadget, SPH simulations by Avishai Jekyll and Ramil Dave and collaborators that argue that ULERGs at high redshift could actually be just normal disk-type galaxies with high gas fractions and not merging at all. So, and this is also reinforced by some observations of higher gas fractions in galaxies at early times. This is just a plot of the H2 gas fraction in galaxies as a function of redshift, and you see it's dramatically different. It's almost 50% of the baryonic mass at high redshift. So with high gas fractions, you could theoretically sustain very high star formation rates for longer periods in relatively steady state. Another argument, more indirect argument for this, is this supposed main sequence of galaxies, which is an observation of a tight correlation between star formation rate and stellar mass. And the fact that this relationship evolves with redshift. So at higher and higher redshifts, the star formation rate per a certain stellar mass are much higher. And since the relation is as tight as it is, this means that stochastic events can't dominate the processes going on in these ultraluminous systems, or else you wouldn't see the correlation. And so this argument has been used in some cases to claim that all galaxies that sit on this relation are normal galaxies. So this kind of causes a little bit of a contradiction in that the main sequence of galaxies argument redefines normal, what's normal at high redshift. So while these ultraluminous infrared galaxies at redshift 0 are all these extreme mergers, you would have to look at much more luminous systems at higher redshift to find the equivalent class, and that more normal galaxies at high redshift are now equivalent in luminosity. From the simulations perspective, there's been various conclusions on this from SPH and now Arepo, where the IGM, in one picture, the IGM is dense enough where gas is fed directly via filamentary flows onto these galaxies, sustaining high star formation rates. But perhaps more recently, in another picture, gas, even though it's dense enough to be fed onto the dark matter halo, is heated up and cannot be fed into the centers of galaxies where they can form stars so efficiently.
Actually, the rays are even higher in that book, so in both cases it ends up in this.
Right.
Details are different.
Yeah. Of course, you're the expert in this more than me. But the point is that neither the simulations or the observations really agree on the evolutionary interpretation of these extreme systems. But first, to get a better idea from the observer's perspective of what is happening within these galaxies, you need to have an accurate census and have a really good understanding of your population of high redshift galaxies, which is harder than you think. So in this section, I'll go from the motivation to discussing some of the practicalities of observing infrared starbursts at high redshift. So this is an image of the Hubble Deep Field at some millimeter wavelengths. So many of you are probably familiar with this little cutout of the Hubble Deep Field in optical, but this is the equivalent size of the Hubble Deep Field mapped at 850 microns with the original SCUBA instrument, the sub-millimeter common user bolometric array at JCMT, which is shown here. And so this originally came out about 15 years ago, but it was really groundbreaking in that for the first time, these sub-millimeter bolometers had enough sensitivity to detect galaxies at high redshift that are equivalent to these ultraluminous infrared galaxies. You might notice an obvious problem in that this is much more difficult to interpret than galaxies in the optical, and I'll get to that. Okay, so sub-millimeter observations have a great benefit in that they have what's called a negative K correction. So as you push a galaxy back in redshift, because of the shape of the SED, the flux density of the galaxy is not changing dramatically over several over a wide range of epochs. So this is a just cartoon of an SED. This is your reprocessed dust emission in the far IR, and then this goes out to the radio synchrotron emission. But what you should notice is as I push this galaxy of fixed IR luminosity and dust temperature back in redshift, here we're just starting at 0.5, what happens to the flux at this blue wavelength, 850 micron, as opposed to the flux density at 24 micron or radio 1.4 gigahertz. So as you push it back in redshift, past redshift 2, 3, 4, the flux density at 850 micron doesn't change a whole lot. It might change by 1 dec. But here you get a dramatic fall off, and in radio wavelengths as well. So what this tells you is that it's actually, if galaxies emitting in the sub-millimeter are out there at very high redshifts, we'll detect them in the sub-millimeter. So it just plots the K correction of a whole suite of bands, highlighting how at this sweet spot in the purple bands here, around 1 millimeter, a galaxy of fixed luminosity will have roughly fixed flux density out to even redshift 10. So now let's go from our blobby map to actual real galaxies we can try to understand. You'll notice, of course, that the beam size is huge at some millimeter wavelengths and very difficult to interpret. When you look in the optical, there might be 10 to 20 galaxies that fall within that beam, and you have to know, well, you know, this is one bright source, or is it multiple sources within the beam? It's difficult to entangle. So our end goal is to characterize the systems emitting at some millimeter wavelengths, but to do that, we need some basic characteristics like star formation rate, gas mass, depletion time scale, stellar mass, et cetera, et cetera. We need to measure all of these quantities, and to do that, we of course need redshifts. So that sounds simple enough. How do we get a redshift for a sub-millimeter galaxy? There are two pretty common ways. One, of course, which many of you will be familiar with, is to go with your very large optical telescope or near-IR telescope and look for it with your favorite spectrograph. And the problem with that is that we obviously don't have the resolution to know which source is our target in the optical or near-IR. And second, the second alternative, which is very exciting, is that we can search for CO lines in the sub-millimeter on the Rayleigh Jean's tail and try to understand what the molecular gas emission is looking like. But the issue here is that when we search for CO lines, we have a fixed bandwidth, which in the years pre-2011 was pretty narrow. And so it was very difficult to serendipitously discover a redshift for a source. So this issue of confusion noise is what I'm describing by a large beam size. It's just when you don't know which source to match to because the density of your emitting sources is greater than, much greater than 1 over the beam size. So how we handle this, in the optical, it's kind of a minefield, but we use this trick, at least in over the past decade or so. This was what was primarily used, is we looked in the radio wavelengths, and we can use this very handy empirical relation, which has observed that the far infrared luminosity of a source maps pretty well and tightly with the radio luminosity. So if this is emitting in the far IR, it should be emitting in the radio, and we should be able to detect it. And in radio wavelengths, you have high resolution because you've used an interferometer. So that gives us the precise positions to then put slits on our target and then go get the redshifts with, say, Keck. And this is, by and large, what was done in the early 2000s by a bunch of my collaborators, the original SMG team, Scott Chapman, Ian Smale, Rob Iveson, and Andrew Blaine, who had about hundreds of these SMGs in a few square degrees mapped by scuba. About half of those had good radio identifications, and then about half of those had good rest optical or UV emission lines, which enabled us to yield redshifts of the SMG population, the millimeter galaxy population. And that was really the first time we had a good constraint on where these sit in redshift. We found that they would peak around redshift 2, 2.5, which is near the peak epoch of star formation rate density. So clearly something interesting is going on here. Here's a slightly updated redshift distribution.
So, in your picture before, so there's a clear radio source.
Yeah.
Which has a smaller beam. But then when you look at the optical image, it didn't look like there was a source where that was.
Yeah, no, that was that's often the case. So about half of, like, you know, we'll have a precise position for the radio source, and following it up in the optical, it's often done like blindly, where there might be a counterpart at IRAC, you know, near IR wavelengths or maybe K-band. And it might be almost completely extincted in the optical, but we're hoping for that detection of an emission line, which happened like half of the time.
Okay.
So.
And then, I mean, maybe you'll get this, but only half of them had radio detection.
Yeah.
So you're.
Yeah.
What's going on with you?
Yeah. No, that's no problem.
Okay.
So with redshifts, we were able to create kind of a holistic picture characterizing some millimeter galaxies. From CO observations, X-ray. So just to step through the characterization that was done over the last decade, many of these were observed in CO molecular gas in all sorts of transitions. Here's a excitation spectral Hawaiian energy distribution diagram for some millimeter galaxies. Quasars are typically very excited. Milky Way is not so excited. SMGs sit somewhere in the middle. But if we look at their kinematics, they often show very broad line widths and very disturbed kind of morphologies, which is not straightforward to get out of the optical because these are so dusty and extincted. So this is evidence for actual mergers at high redshift in some millimeter galaxies. If we look at H-alpha kinematics and just line profiles, we find the AGN fraction is pretty low, less than 30%. High velocity dispersion, high dynamical mass, short duty cycle, and SMGs are dispersion dominated and highly asymmetric. Again, signatures for mergers.
How would this look for minor mergers? Can you rule out minor mergers?
So there are some SMGs at the very top of the luminosity function, and they all look like this, and this is kind of clear evidence for major mergers. You need a major merger to produce this type of kinematic profile. There are, I would say, on the fainter end of the submillimeter galaxy population, it's less straightforward. Their X-ray properties are what you would expect of mostly star-forming galaxies. For a while, there was kind of the thought that, oh, well, AGN are or quasar-like luminosities are contaminating what is otherwise thought to be star formation. So maybe these aren't such extreme systems after all, if they're just quasars, but that's not the case. Only about 20% of SMGs contain luminous AGN, and their volumetric luminosity is still dominated by star formation. In the mid-infrared, we've looked at them as well with Spitzer IRS, and this is spot on with what was found with X-ray and H-alpha in terms of AGN fractions. We see strong emission from polycyclic aromatic hydrocarbons, PAHs, and that's totally consistent with strong star formation and relatively little contribution from AGN. If we look at the rest frame UV optical characteristics, we see that the spectra are very dust extincted, and they're very difficult to detect, which is why some of this work is still coming out years after the original spectra were taken. This is just a plot I made recently for our review paper coming out next year on some millimeter galaxies with a stack of H-alpha, O2, and Lyman alpha for some millimeter galaxies in comparison to a more typical Lyman break galaxy. What's important to know here is that the star formation rates from the optical and UV underestimate the total star formation rate by factors of 10 to 100, which is pretty dramatic. I mean, these are extreme dusty systems, but even our best guess as to the extinction from the optical does not correct for that. Okay. So all of these characterizations have been very useful to kind of lead to the conclusion that most submillimeter galaxies are major mergers, totally consistent with the earlier picture coming from the local infrared luminous galaxies. But there's a big but. Sample sizes have been really small. I would say 5 to 20 galaxies total have been studied in really exquisite detail, with about 70 total having gas mass measurements, and about another 100 have basic data. So this is the pre-Herschel days, and the samples have been really limited, and there are bad selection biases which persist. The first selection bias, which Allison referred to here earlier, is this radio emission bias. Basically, anything that has a spectroscopic redshift that's an SMG, initially that was followed up, had to have a radio ID. But the radio doesn't have the benefit of submillimeter observations in that it has a positive K correction. So as you go back in redshift, the flux density plummets like a rock. So you can't really easily detect systems at very high redshift in radio mounts, like you can in submillimeter. So if you put the radio criterion on your sample, you're not going to detect the very high redshift systems. So that's an obvious bias. So when they say submillimeter galaxies peak at redshift 2.5, that might not be the case. There could be a population at much higher redshifts. Dust temperature bias. This bias was the focus of my thesis back in the day before Herschel, where if you observe a galaxy, or if you try to find submillimeter galaxies just at 850 microns, which is on the Rayleigh-Jeans tail of the black body, you're going to potentially miss a large number of systems just due to small variations in the dust temperature black body. If you have a SFR, star formation rate limited sample. So at about redshift 2, the flux density at 850 microns scales with the luminosity times the dust temperature to the -3.5 power. So it has a very strong dust temperature dependence. And this could potentially miss a very large fraction of infrared luminous activity at high redshift. And just to give you a better idea of what's been happening more recently, many new observatories have come online in the far IR to fill in the previous bias of 850 micron selection. And what I'm going to talk about next is the Herschel work at the Spire instrument at 250, 350, and 500 micron. But you can see there's really increasing coverage all throughout the far IR which will give us a better idea of completeness in these samples. The Herschel Spire instrument has been amazing for mapping very large areas of coverage, unlike the previous SCUBA instrument. This is that original image of the HDF, the Hubble Deep Field from SCUBA, and just to give you an idea, this is one field of coverage by the Herschel Spire instrument. So they're mapping hundreds of square degrees with, they have mapped hundreds of square degrees with Spire. And as a result of mapping hundreds of square degrees, you can do much more large-scale follow-up with these systems. So my time in Hawaii was largely focused on following up getting spectroscopic identifications for Herschel selected samples, just like the 850 micron SCUBA selected samples, but you're picking them on the peak, so you're not biased with dust temperature, and you're going to find more systems in the gap between the most extreme systems at redshift 2 and 3 and local ULERs. So it's slightly lower redshift.
Are you still constrained by radio identification?
Radio or 24 micron. So lifting the radio identification, any way you can make it slightly better helps. So requiring 24 micron is fine if you're looking below redshift 2. If you're going above redshift 2, it gets a little more hairy, but that's been a difficult problem to solve. So the key advantage with this sample so far has been just the huge areas that Herschel covers. So increasing the sample size quite a bit, not necessarily removing all of the biases. But the results of this, which came out late last year, have been that we've been able to increase the number of spectroscopic identifications for infrared selected starbursts by tenfold, from about 70 galaxies to around 800 galaxies. So it's a great sample to work with, in particular because these are not in your typical large spectroscopic surveys, because they are very optically faint. And only about 30 to 40% of them would have been detectable with SCUBA.
How long do you have to integrate to get?
A few hours, yeah, to get a bright emission line. We're not going for continuum at all. Yeah. So results in terms of the star formation rate density as a function of redshift from the infrared perspective alone, just to show you the contrast of what Herschel has brought to the table. I'd say, in 2005, this was the picture from the IR perspective. We had good estimates out to redshift of 1 from, say, Spitzer, and then beyond that, we had really incomplete samples from some millimeter surveys from the original Chapman SMG surveys that were far down here. And now in 2013, we've been able to fill in a lot of this gap with Herschel, trying to understand the infrared contribution to the total star formation rate density. So it's actually indicating that, like one would think, with half of the light being emitted in the optical and half in the infrared, it's what the star formation rate density also looks like. Half is coming out in the optical and half in the infrared. So. There are great follow-up studies we've been able to do on Herschel samples as a result. Really stuff that hasn't been done before in terms of understanding far infrared selected samples. These are 2 projects I was working on while at the IFA with grad students Nick Lee and Xiaoling Hung. The first is to understand the SEDs of far infrared selected sources from Herschel in a totally empirical manner. So these SEDs are completely data-driven and involve no model assumptions. So this is like the first time we've been able to probe the peak without blindly trusting a template in the far AR. And Xiaoling Hung's work here has been investigating optical morphologies from ACS and Cosmos to try to understand where infrared luminous galaxies, if they're merger dominated or not, as a function of where they sit on the main sequence or star formation rate stellar mass relation. And what she finds is that merger rates, although they are significantly increased when you are above the galaxy main sequence, they're equally correlated just as a cut in luminosity by saying increasing the luminosity, you increase the merger rate, rather than necessarily more highly correlated as the ratio of star formation rate to stellar mass. So the elephant in the room with Herschel is that it has really bad resolution. It's great for large area, but lousy for resolution. So it still has this problem of not knowing what counterpart is correct. So one way to fix this is to look at the same type of wavelength, but use a larger dish, which is done here on the ground at JCMT again, but with the second generation SCUBA instrument, SCUBA 2, which has a 4 times increase in bolometer arrays and large area scans. And the most important aspect, I would argue, is that it now has mapping capabilities at 450 microns, in addition to the original 850. And the beam size at 450 is half that of 850. The observational difficulty is, of course, the atmosphere is very opaque at these wavelengths, so you need the best weather to observe at 450 microns. So just to show you, illustrate the contrast between the resolution of Herschel's Fire and SCUBA 2, this is a cutout from the Cosmos field at 500 microns with Herschel, and virtually the same wavelength, 450, with SCUBA 2 with a much smaller beam size. So you can see individual sources with uncertain positions really resolving into nice pinpoints. Yes?
So far with the weather, how many days of the year have you been able to observe?
So this weather only comes around 5 to 10% of the time. It's very difficult to get. But this winter, or the winter of 2011, 2012, we were incredibly lucky, which is great because it was when the instrument was originally commissioned. And we had this map to get to 4 millijansky RMS took 33 hours to make. So the fantastic thing about it is that the resolution, as good as Spitzer 24 micron, gives you a huge advantage, so you know your counterpart and you don't have to do this silly matching to the radio or 24 micron game. And this is kind of the precursor to the CASS telescope, which is going above the ALMA site relatively soon. Just to show you briefly one result from this work, we have been able to resolve SMGs into multiples with SCUBA 2, just like work that has been done recently at ALMA and other interferometers that shows that maybe some millimeter galaxies aren't as extreme as previously thought. If you attribute all of the flux to one system, then these would be very, very extreme. But when we resolve them with higher resolution, they're breaking up into multiples. And this perhaps has big implications on whether or not these are mergers or not. And we see the same thing with SCUBA 2, which is rather remarkable because it still is a single dish bolometer telescope. This is just one example of a 450 micron source, or an 850 micron source splitting into two 450 sources. So now I'm going to step away from the practicalities of studying these infrared sources and the difficulty to speak about the future of where this is going and how we're going to get rid of some of these biases and problems that have plagued the field so far. So what's next? So ALMA, of course, is a big part of this. Since these are infrared luminous galaxies, you want to look directly in the infrared to detect them. So ALMA provides direct detection on resolved scales of the dust and gas. So you can couple that with the star and the starlight coming out in the optical to get a holistic picture of what's going on.
Caitlin, for these sources where there's multiples,
Yeah.
What rough scale are we talking about? Like what physical scale?
So these are resolved on like arc second. So this whole beam size is about like 17 to 20 arc seconds. And so a resolution of an arcsecond gives you like 8 kiloparsec scales. So these are individual, separated systems. They might be associated.
Yeah, and like, is the typical separation like a megaparsec or like?
No, yeah, just no, less than that.
Okay.
Yeah. These are if they're associated, they're very close.
Okay.
Like if they're at the same redshift, but we don't have spectroscopic IDs for
They probably
the vast majority.
are. Well, probably.
Yeah.
I mean, even just given how clustered they are.
Right.
Even at lower redshift.
Well, the thing is, there's also a selection bias here of, we've only targeted. Yeah, I agree, but there's also the selection biases that we haven't targeted blank field sky. So these systems, if they weren't next to each other in the sky, wouldn't have been detectable from the large beam size bolometer.
Right. No, I don't mean to
Right.
say that this is what's going on with most.
Right.
SRG, but just the ones that have resolved into multiples,
Mhm.
probably statistically most of them actually are in the same redshift, just given how close they are.
Right. I
Doesn't mean
I'd
that
guess.
they're right.
Right. So ALMA can be used to, you divide, see if there are multiples, and if you have unambiguous counterparts, that's great. You can also measure the global gas mass evolution up to a high redshift to understand the gas fractions. And
Is there any way to get the redshifts of the individual components there in those things? Or is that?
yeah. So I've been working to get them with Mossfire, target these individually. It's difficult to get 2 in one go, so you often get 1, and then you have to go back and get the second one in another mass. So we're working on that now with Mossfire.
Why is, I'm sorry, why is it difficult to get to?
Oh, just, these are separated by, an arc second, maybe 2 arc seconds.
Oh, I see.
So, it's
Since you're
aligning the
close to
split and also taking in mind that you want to get species for the other sources of the field.
Just a comment, there are examples where people see situations like this and there are indeed very different redshifts.
Yeah, there are.
Examples in the picture, so not really clear if these are the same.
Right.
Just because you can see SMGs at any redshift.
Right.
Oh, yeah. Okay.
Yeah, that's.
Because optically, like 90% of those would get.
Yeah, no, it's not really.
Okay.
Yeah, because the flux density would be the same.
Yep.
Okay, very high redshift. So in addition to measuring the gas mass evolution, you can do very detailed kinematic studies. This is a really exquisite system at redshift 4 of a rotating disk galaxy, which is a very bright simulator source called GN20. And you can do really exquisite dynamic studies of these systems. You can also image blank fields of sky. It's not going to be, ALMA is not, a blank field mapper in the formal sense, because you can only do very small areas. The field of view is effectively very small. But over small areas, you could go very, very deep and do a blank field, and this is what Jim Dunlop is undertaking in the UDS. Another technique is you can try to spectroscopically confirm SMGs using this blind CO technique, which you can take advantage of the wide bandwidth, and in a couple of observations, you can go through a huge wavelength space to detect your CO lines. And in addition to CO, or to ALMA, sorry, the CCAT telescope is really essential for pushing the boundaries of this work. CCAT is a 25-meter dish, basically a bigger version of JCMT, which is currently on Mauna Kea, and it will be mapping far infrared wavelengths over large areas of sky from 200 microns to 2 millimeters. And particularly at the shorter wavelengths, it's going to have a very small beam size based on the size of the dish. So that's going to be the next generation. In the shorter term, we're also looking at extinction and trying to understand how the optical properties or the starlight relates to the dust and gas, which is emitted in the far AR. So we're really trying to empirically, carefully relate what we see in the far AR to what we see in the optical. And this is work which is furiously in preparation right now with a few students I've been working with. The next generation of this is, of course, with the 30-meter class telescopes like TNT, where we can individually really classify and get a high signal noise spectrum for some millimeter galaxies and high redshift, and have optical diagnostics for AGN and outflows, and confirming the redshifts out to even higher redshifts, redshift about 6, less than 6, and spatially resolved ionized gas kinematics. So it's an exciting era from the optical near IR perspective as well. And just to show you an example from Mossfire, from spectroscopic confirmations from Mossfire, and a comparison to the same effort in the optical. So after a couple of hours integration on some millimeter galaxies in the optical, I would consider myself lucky to get this kind of emission line detection out of one out of 4 systems. So that's worth celebrating. But in Mossfire and the near IR, since there's so much less dust, we can easily spectroscopically confirm SMGs via rest frame optical lines like H-alpha. So this is really an exciting time for spectroscopic follow-up of SMGs. And not only that, you get the dynamic profile of H-alpha as well. So stay tuned for more results on that. So in summary, what we've learned is that the starlight is great for teaching us about what's coming out in the optical, tells us our unobscured star formation rate, extinction, star formation history, stellar mass, morphology. But to really have a holistic picture of galaxy formation, you have to also look at molecular gas and dust reprocessed emission. This gives you your obscured star formation rate, dust temperature, dust mass, ISM mass. Molecular gas gives you your gas fraction, or what your star-forming fuel is. And this is the area where I've been focusing most of my work over the past few years. So the long-term goal here is we want to raise the profile of dust and gas analysis to the same quality as all of the optical studies over the past 20-something years. And to do this, we need tens of thousands of galaxies identified in the IR to build large statistical samples. Now, time for something completely different, really quick. I wanted to put in this quick plug for a piece of ours, which is coming out in Nature tomorrow, in the careers column, entitled The Ethical Gray Zone. This is an exercise which, well, I think it's important to raise this issue in the context of science discussions, and so I've been doing it as much as possible. This is a exercise that Kartik Sheth and I ran at the Aspen Center for Physics this past summer during a Galaxies Evolution workshop on diversity and ethics in the field, addressing issues like plagiarism, bullying, harassment, unconscious bias in our community, and trying to do it in a non-confrontational manner. Because we're not trying to blame anyone for having bad behaviors. It's like to improve the field, you really need to, and improve the working environment, you need to discuss what has actually happened. So just a bit plug for that. It's coming out tomorrow. Surely will stir a bit of controversy, but it'll be interesting. And another, we are having a follow-up post on Faster Better on Monday. Okay, back to science. My conclusion slide. IR starbursts are really important, and to figure out what the dominant mode of star formation is in the early universe. And to do that, you need large statistical samples that have high resolution and are unbiased. Thank you.
Questions for Caitlin?
Can I ask another elementary question? I always have to inform, I'm sure you've heard before that. I'm just a lowly biochemist, but I love to come to the astrophysics seminars. But you mentioned this empty space. Now, is there some definition for that, like lower than some number of objects that are emitting in whatever wavelength you're looking at that define what empty space is? I mean, because obviously it's not completely empty. You showed what appears to be a bunch of stuff.
Right. There are lots of voids in the universe, surely. And well, these galaxies exist in different environments. So there are environments that are like galaxy clusters,
Right.
and there are
Looking at deep
filaments.
fields, you're looking at galaxies, so yeah.
Yeah, but they're technically, they're in the field. There might be clusters hidden in that. Technically, you're looking at a 3D cube, so there could be little clusters, at low redshift and some at high redshift earlier in the universe. So there's a variance, yeah.
So,
Yeah. Oh, sorry.
so you asked mergers or not, so how much of the star formation is having clue at this point, or do you have to wait for?
Not at high redshift, no. I mean, we need complete samples to do it, and we're far from that. And you need to be very clear about your sample selection. So from the submillimeter galaxy classical perspective, yeah, they're all major mergers, but there are these selection biases which plague it.
When will we know the answer to the question?
When will we know?
How many years?
After we have CCAT.
So we need CCAT,
I mean,
coming online for 2017 or something?
Right. We can form a pretty elementary picture of what's going on at the very highest luminosities now with what we've gathered from Herschel and Scuba 2 and the LMT in Mexico as well. Yeah, I think to raise it to the same level of quality of data as what we already have in the optical, it's going to take CCAT. So I mean, ALMA provides a lot of the answers, but it doesn't solve everything.
So take your favorite Euler and
Mhm.
find some 10 to 20 optical galaxies within that same footprint of this older data for ALMA.
Yeah.
You take some number of radio detection, some number of infrared, micron detection. If you were to add up the estimate of star formation from all of those, you still don't get the star formation from
No, so the radio does a really good job. 24 micron can do a good job, although it has much more, it's less precise of a relation. No, the issue you get is when you're looking in the near IR and optical and rest frame UV. Basically, you have galaxies which are very millimeter bright, but in the optical, they look virtually normal, like just normal, everyday, run-of-the-mill Lyman break galaxy. And it's only because we had that observation of that galaxy in the submillimeter that we know it's 1,000 solar mass per year system. Because in the optical, even after correcting for dust, it might only have a 10 solar mass star formation.
But the combination of a whole bunch of galaxies within your PSF isn't adding up to make those.
No, it wouldn't. Yeah, I mean, in the case of these multiple SMGs, which might be 10 to 30% of the whole sample, that fraction needs to still be constrained. You do get these star formation rates to add up in a reasonable way. So what you originally thought was, 2,000 solar masses per year does break up quite cleanly into multiple systems, but only when you're looking in the far IR directly.
When you're, if you're moving over to 450 better resolution, what biases does that induce in terms of sensitivity to the targets? I mean, are you losing sources because they're 850 bright?
Yeah. At highest redshifts, you do. So it's a trade-off. I mean, at 450, you're pretty sensitive. I don't know how I escape this and go back to. Let's see. Yeah, I commented on that as a pretty, that's a keeper. So at 450, let's see, that's cyan. The K correction is kind of, it's not really negative, but it's kind of flat. So you're going to miss out on the highest redshift systems, and it's going to be relatively less sensitive towards the redshift 4, 5, 6 systems than the 850. So one thing, I mean, the flux density overall is much higher at 450, but the sensitivity of the instrument is not making up for that.
So, when you identify these sources and you chase after them with some high resolution, submillimeter thing like ALMA or CCAT,
right.
One of the things you're looking for is, are there companions, are these systems?
Yeah.
But if you've got let's say a quiescent galaxy that's not really amped up
Mhm.
like the other one. If you have a prograde retrograde system, the prograde might light up and the retrograde not. So
Right.
Can you see a normal galaxy that's not really?
Yeah, we see this a lot actually. It's kind of really frustrating for like us if we're trying to characterize it in a straightforward way. We often see like pairs where one system is completely dust obscured and has virtually all of this millimeter flux, and the other is optically bright and is the millimeter faint. And yeah, the star formation rates are high in both cases, but they have very different observational manifestations.
But are they detectable in the submillimeter?
If you have very high resolution like ALMA follow-up, yeah, it might be, but predating the past few years, no.
Because the point is that you might misidentify
Mhm.
whether it's an emergent
Yeah.
system or not because you just can't see the other one because it's not
Exactly.
being lit up.
Yep.
I just have a question about the extragalactic background light.
Yeah.
So are you basically saying that lurks, how much do lurks contribute to the optical? Did you say it's mostly normal star-forming galaxies that dominate the optical background?
Right. Yeah. I mean, they're much more moderate, than these 1,000 solar mass per year systems.
So they have to be numerous, many tens.
Yeah.
Magnitude, of the.
They're much more
the
common.
infrared
Yeah.
To be even defined.
So if you have like.
Because they're all emitting something.
Right. If the star formation rate is down by a factor of 100 compared to the extreme systems, then you have to have 100 more galaxies to make the same contribution. But overall, they're making more of a contribution in the local universe than these extreme systems, even when you correct for them. But in terms of like the overall infrared background, the CIB is largely dominated around like out to redshift 1, these blurred type systems. And the contribution from higher redshift galaxies is relatively small, but it's
From
higher than to the CIB is relatively small. But you can place good constraints on the distribution of high redshift sources based on number counts of the CIB.
Okay.
So, can I ask an elementary question? You mentioned something about, I always ask the chemistry question. You said, I don't know if it's significant or not, but something about multicyclic aromatic hydrocarbons.
Yeah.
Now, are those,
pH.
what would we need to say about that?
Those are just very heavy dust grains. They have several hundred carbon molecules.
Like the origin of life, if you can have those complex molecules out there getting zapped by high, high energy photons of all sorts,
Right. Yeah. No, I mean, so it's we use those to study like the dust properties, and we found it correlates very well, like emission from those lines. It correlates very well to the total star formation rate, but also the ratio of the different lines can tell us, about the temperature and how cold the ISM is, and whether or not it's more diffuse or more compact.
Right.
And that can tell you something about, indirectly, I guess, whether or not it's more likely to be a merger if the gases and dust is more
So someday
diffuse.
you're going to be studying Andromeda merging. Well,
Yeah,
in the
exactly.
future. Thank you very much.
Yeah, thank you.
Okay, before we thank Caitlin again, we just have this custom to give us the
Yeah, sure.
check to the
Sounds
speaker and I just heard, so let's thank Caitlin.
Quickly, you exhaust all of the gas, and then you have no more stars to form. Perhaps a black hole kicks in, and you have AGN feedback, which expels gas, and you settle into an old population. So again, locally, all infrared galaxies, all ultraluminous infrared galaxies are mergers. But the question we want to answer now is this the case at high redshift? So this is a schematic of the star formation rate density with redshift, or Lilly-Mandel plot, where you have contributions from different populations to the star formation rate density of the universe. At redshift 0, these U-lurgs and lurgs contribute very little to cosmic star formation, but these are known mergers. at early epochs in the universe, past redshift 1, they actually dominate, they contribute significantly, if not dominate, the total. Yes?
They've already gone through a significant amount, the Ulrich of star formation. In other words, are they in the post, sort of like you said, they don't contribute much?
Yeah, they don't contribute much at redshift 0. So in other words, they're just very rare. Normal Milky Way type galaxies are forming more stars per unit volume.
They did a lot of star formation.
Yeah, so I mean, what was a ULIRG at high redshift is no longer a ULIRG because the time scale for that phase is very short. So the question is, since these are so important in the early universe, are they also mergers? Another question we want to address is what the contribution is at even higher redshifts. So there's good estimates from the optical do large.
Okay, so I think we can start. So it's a pleasure to announce Caitlin Casey. She's now our neighbor at UC Irvine, and she finished her undergrad at the University of Arizona. And after undergraduate degree, she went to the University of Cambridge as a prestigious Yale scholar. And after finishing her PhD in Scott Chapman, working on 7-meter galaxies and highly ULIRGs, she got another prestigious Hubble Fellowship and moved to University of Hawaii. And after expiring her Hubble, she's just starting a new fellowship at UC Irvine called McHugh Fellowship in Cosmology. And she became well known in the field by her work on warm ULIRGs and a bunch of properties of 7-meter galaxies, started from her thesis, and then I guess she increased sample of 7-meter galaxies and warm ULIRGs by an order of magnitude or so, and she's been working on all kinds of issues related to very star-forming galaxies and high edges, and she's going to talk about them today, and I guess her title is Mergers or Not. So
great, thanks, Tushan. Yeah, so I decided to make my title as controversial as possible. This is a big debate in the area whether or not infrared luminous galaxies are all dominated by major mergers, or if you don't need major mergers at all to explain infrared galaxies in the early universe. So yeah, it's great to be here today at UCSD. It's a pleasure to talk to an audience which is pretty diverse. You know, I know some of you are experts in galaxy formation and evolution, but others of you are experts in other things. So I really like it, you know, since it is a diverse group, if you just go ahead and interrupt me if I don't make sense at any point, and it'll be great. I'm always pleasantly surprised when a talk turns into a discussion. So what I want to discuss today, evenly split. So what type of galaxy emits in the infrared, and is there any reason to think that they're different than those that emit in the optical? The initial study of infrared luminous galaxies started, I would say, with the infrared astronomical satellite launched back in the 80s. This is a great facility discovering thousands, many hundreds of thousands of point sources all across the sky, most of them nearby, really exquisite systems emitting in the infrared. And when we looked at the same places as the sky, in the optical, what we saw was that nearly all of these galaxies were major mergers. All ultraluminous infrared galaxies, nearly all, are major mergers. And just to throw some terminology in front of you now to avoid it later, you'll often hear these terms in the high redshift dusty galaxy world. LIRG, luminous infrared galaxy, that is a system that has an infrared luminosity of greater than 10 to the 11 solar, or about, you know, a few 10 solar masses per year star formation rate. ULIRG, ultraluminous infrared, and high LIRG, hyperluminous infrared. So those are the classes of infrared luminous galaxies split by luminosity. And then in the high redshift world, we often talk about some millimeter galaxies, which is a term that's often used loosely. It can have a strict definition, but it just refers to any ULIRG type system at high redshift detected in this millimeter. So over time, after we studied these local systems in detail, the schematic evolutionary diagram was developed to explain these very dusty starburst galaxies. And this was presented rather concisely and well by Dave Sanders in '88, where you have two merging gas-rich disk galaxies, not unlike the Milky Way, that collide and ignite a very heavy episode of star formation, and where there's a lot of production of dust. And this is what's called the Euler phase, when a lot of the emission from young, hot stars is absorbed by dust and re-radiated in the infrared. And so that's the Euler phase. And after that phase, you might have a black hole, which is accreting material, a supermassive black hole, and obscured AGN or an unobscured AGN leading to a quasar. And after the black hole stops accreting material, you might settle into a massive early type elliptical galaxy. So this was the explanation for the formation of local elliptical type galaxies. And this is what I refer to as a classic evolutionary scenario for ultraluminous infrared galaxies. And it really came about from that IRAS sample. Looking at it a bit more quantitatively, this is a schematic of the star formation rate against cosmic time. From the early pre-merger stage, you get star formation rates of a few tens, maybe 100 if it's a star-forming galaxy. But during this Euler phase, which is very short-lived, you get incredible star formation rates, which often exceed the star formation rate previous to the merger by factors of 10 to 100. But since the star formation rate is so quick that maybe you use up all of your star-forming fuel very quickly, I'll split up into three sections. The first of which I'll explain some of the motivations for why it's interesting to study starbursts, infrared selected starbursts in the first place. Second, I'll discuss some of the practicalities of studying infrared starbursts and some of the difficulties and observational hurdles that we experience. And last, I'll discuss the future of submillimeter surveys in resolving cosmic star formation out to very high redshift, and what dust really means in terms of the entire cosmic star formation rate density of the universe. So motivation first. We know that star formation takes place in dusty environments. We see this in our own Milky Way, but also beyond the Milky Way, farther afield. This is a schematic of the cosmic background radiation. You're probably all too familiar with the cosmic microwave background, but there are also these components emitted in the optical and the infrared, which originate from extragalactic sources, galaxies. And we've come to know quite a bit about the cosmic optical background from facilities like the Hubble Space Telescope, which sheds great light on cosmic star formation out to very early epochs in some of the earliest galaxies. But when we look in the infrared, we've been much more limited, to be honest. And this has been due in part to limitations in observing. But what we want to do is kind of move into a realm where we understand the infrared component just as well as we understand the optical component, since the relative emission in both regimes is